So you've had an earful of imaging 1, 2, 3. So let me put another whole reason why we do this. One is clearly we want to say that, as Dan Whitmore said, it's not that Claerbout II can't give you any amplitude information. You have a speculative reflector. Thanks to many people that I mentioned here, it can give you a geometric optics reflection coefficient. So it's for you to decide under that circumstance, is an actual reflection coefficient versus a geometric optics reflection coefficient, is that difference that you saw of use, yes? And if it is, then do Claerbout imaging 3, yes? That's a decision based on what you want to do with the reflection coefficient. The other is for non-speculative, that's they totally separate. You can do imaging with structure and amplitude analysis where there is no reflection coefficient. There is no plane wave reflection coefficient or geometric optics. You can assume what you want, but when it's this and that, there's no reflection coefficient. So for that, Claerbout III brings you something new. What you just saw, Chung Fu's show, is you can image under a reflector. Claerbout II cannot image under a reflector. You're not going to get a geometric optics under. Okay? You're going to get above for a reflector. Now, so what's the use of that? What's the use of imaging below? Well, let's say you have a pre-salt, and you image this way, and you image that way. You can place with a Claerbout III your experiment under or above that target. Yes, you have two different. Yes, you can. We leave you with that. The next and very important reason that we are talking about this is what we're going to be talking about tomorrow. This group, as we started this meeting today talking about, and we'll be talking about tomorrow, is known for removing multiples. So what does that have to do with this? So that's what we're about to tell you. People of high integrity and capability have been talking about using multiples, yes? We hear from people, including among our sponsors, that you don't need to take multiples out anymore. We have a new holistic, inclusive, politically correct view of seismic, yes? You understand? And all our events are going to be treated with respect and given equal opportunity and so on, yes? And so that's a very serious statement. The people who know at PGS and Schlumberger will never say that, but I've heard that. I've heard that from more than one oil company, yes? So part of this conversation now, why do we want to talk about Claerbout imaging 3 relative to that? Nothing is as definitive in terms of what the image means. Yes? You put a source and receiver there and ask critique equals 0. It's not looking at both Claerbout II and Kirchhoff. They have ellipses with possibilities that have to add coherently. Yes? There's a vagueness there that if you're trying to say, are multiples used in imaging? Well, maybe not here, but maybe up on the tail of the ellipse, you know? Here it's, at this point, is there a reflector or not, and which events contributed to that image, period, yes? So for us, having a way to do Claerbout imaging 3, that experiment, in a world where waves could be up and down, is going to give us an answer to the question, which events in this most definitive of imaging principles contribute. So, understood? We're going to take you through watching how events with multiples, what happens when you image, what happens when you predict the experiment, and then what happens when you image. Yes? Then after we finish with that discussion will give a definitive answer to that question. Then after that, we're going to talk about what is the value that we see for using multiples. Yes? And does that mean if you're using them, do you not get rid of them? You get rid of them. You understand? People say that's mixed up. We're going to show what we view as the new seismic tree, because all the methods that are using multiples require a velocity for the primary that you did not record, that you hope to get an approximate image of. You repeat that. You need a velocity. You see it, yes? You can't get okay? There's a primary that you did not record that's with a sub-event of the multiple that you're trying to get an approximate image of. That's a worthwhile enterprise. Why? Because there are always primaries that we don't record, that we'd like to have. Yes? So the question, though, is how are you going to get the velocity? Well, we know how to get the velocity. The first thing you do is get the multiples out. Understand? So we'll show, you understand? That's the trick. So the point is, you'll see a new tree which says, after you take all your recorded primaries and multiples and get rid of the multiples, right? And we're partially there, we need to do more on that subject. Once you have the multiples gone, then with the primaries that you do record, get the velocity, do a velocity analysis. I know of no velocity analysis that works with primaries and multiples. Okay? You understand? Now, so how are you going to get the velocity of a primary that you didn't record? This is how. You need to have a primary that you did record on the same reflector. Yes? Let's say this primary you didn't record, but some other primary on that same reflector you did record. Yes? And that primary is now available since you got the multiples out. Yes? You get that primary's velocity, and assuming there's not much lateral variation, you use it to find an approximate image of the primary you did not record. Understood? That's why that method will never light something up that's not there before. It has to be there before and then gets longer. That's our understanding. Yes? For the reason I just mentioned. I have to have a primary with that velocity to be able to image a primary I didn't record. Understand? With the same velocity. So you see extended, improved, and we'll show you examples of that. Yes? So the procedure does not require you to, the whole procedure, and you'll see this tree, requires you for an improved structural image to do a very effective multiple removal. So you have primaries to do a velocity analysis. Yes? And then you go back, you'll see in the tree, back up and just get an improved, enhanced structural image from primaries and multiples after you have a velocity. Understood? Okay. So, no, because we hear it from Petrobras, some very senior person there, telling their research is there. We don't need to remove multiples anymore. That's not what you're saying, yes? But that's what they're hearing, and other companies as well. You understand? That's unfortunate. You can understand why it matters to us. If you believe you don't need, well, if you believe you don't need to get multiples out, we can cancel tomorrow, have a good time. Go to council. Yes. In other words, I'm trying to explain why it's still an issue, yes? Okay. So, that's another benefit of Claerbout III. Claerbout III, the definitive nature of what that image means, will now take us, we'll take primaries and multiples and predict source receiver experiment with data with primaries and multiples, and the result will be, if you have events that are recorded, primaries, free surface multiples, and internal multiples, you predict the source and receiver at depth. Every single event in your recorded data will contribute to the new experiment, without exception. But once you ask for small offset and time equals 0, I'm talking about with a perfect discontinuous velocity, right? Once you ask for small offset at time equals 0, only recorded primaries count. We'll show that analytically and through a picture so you can visualize what's going on. Okay, well that's great. It says if you have primaries, that's all you need. That's the reason we're using multiples is because we don't always have all the primaries. But if you had them, that's all you need. Now there are people who say that's not true. That's because of the way they migrate. John Claerbout a long time ago said, when you do these asymptotic forms of migration, whether it's Cherenkov or beam, any variant other than wave, yes, you are going to have an imaging issue. In your migration, you are narrowing a wave to a beam, yes, paraxial ray, for example, yes. So you by your imaging have not allowed the wave to be ubiquitous. John Claerbout said, use wave theory migration, you in principle will never have an illumination issue, in principle. So I just thought to mention that, yes? Okay, so let's go. So this is saying all this that you're sick of already. 1, 2, 3, 1, 2, 3. We have another reason for it, okay? 3 gives us an answer for why we have Friday. Okay? Understood? Okay. Statement here, we're no longer removing multiples. We're migrating. We have a new vision. Yes. Someone can guess my political orientation from probably how I introduce things. Seismic political orientation. Okay. So here's our friend Claerbout III, yes? The guy who says you want to predict an experiment in the Earth where you have waves moving up and down, then you find yourself a Green's function that works in the medium but has a special property that it and its derivative vanish at the bottom. That's all. And let's get to the pictures. So, here's a simple example of a primary. And that's your data. Yes? And then we're going to predict. And predict as the words. Here's the source. So we're going to, it doesn't take a genius to figure out that as this moves down, what data contributes to this. What data? You only have one data. Whatever machine I put that primary in is the data that's contributing to that primary as it goes down, yes? You get my point? What the exercise here is, how do events that you have recorded contribute to imaging? And we're talking about imaging, Claerbout imaging 3, which means predict an experiment and then ask for t equals 0, yes? I'm just reminding why we're talking. So you, does this have a movie? Oh, that's it. That's just showing, we're not moving it down, we're predicting those things, and the same below. So the only event in that data is a primary. So the only data that can contribute to that prediction is the only event that you have. We're together so far, right? So whatever that G0 blah 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 is doing to get that experiment down, and then below, it only had one event to work with. Yes, at the top. Okay, so that's clear. So let's move. So now we'll take an example with a primary and one free surface multiple. Do the same thing, yes? Bring them down. Now you might say, in other words, bring this down. If you just follow this ray picture, right, before the movie starts, Imagine this here. Imagine the source. Here's the actual experiment with this primary and a free surface multiple. Imagine it a little lower. Well, yes. What happens is this event maps to that, and this event maps to that. Why do you say that? Because the whole migration we're doing here is linear. Yes? Green's theorem is linear. We're not doing some inverse scattering series imaging yet till tomorrow. You understand? It's linear. You sum your data. Yes? So each event is on its own going to an output. Yes? Something multiplies the event and produces. Yes? So as everybody understands what they're seeing here. So what happens here, just when you have that source and receiver right above here, this original primary became this primary. And this free surface multiple became this free surface multiple. Understood? So that experiment right above that first reflector, the experiment contained an input from both events. Yes? As soon as you say t equals 0, here's the point. When you say t equals 0, the primary that was like that is now a primary like that. The multiple that was like that is now like that. And you ask t equals 0, this is not t equals 0. This is t equals 0. So the multiple doesn't contribute to the image. Does anyone have a question on what I just said? Okay? Yes? When you go through, it's the same thing. Okay? There's this primary here becomes this primary, and that multiple becomes a new primary, yes, but longer in time. And so, does this experiment care about the primary and multiple original? Yes. When you say t equals 0, only this primary counts. So this goes on and on, okay, with internal multiples, you understand? That's what is going on here. This is an example with two internal multiples, two primaries. That's a mistake. Two primaries and an internal multiple. Okay? And when you bring them down, in each stage, bring them down, when you predict that at this point, these internal multiples here, one will be down like that, yes? This primary here will still be like that, and this primary here became that. So there's only one of those events that when you bring that source and receiver above the first reflector, yes, that contributes to the image. So let me not, okay? That's clear. Yes, you can keep doing that, and there are movies here. The bottom line is, if you have an accurate discontinuous velocity, and you predict with a Green's function, which is that G0dn business, right? You get that experiment. These are two-way waves here, right? So then what you will have is that the experiment at every place cares about all the data, but the imaging condition at time equals 0, multiples will always come in late. Okay? Will never come in at time equals 0. So for discontinuous accurate velocity, yes, multiples do not contribute to imaging. And we're talking about a perfect case here. We're not talking about missing primaries, which is the whole other issue. Yes? This is saying, who, right? Okay. So the okay. So what you're seeing on these slides are that integral, the G0dn making the Green's function along with its derivative, vanish somewhere and being able to predict at different places. What I'm trying to say is It isn't just some movie here, yes? This is validated. That statement, we're giving you a pictorial, yes, understanding of why, for example, when you go, here's you're predicting the field here in a layer. So here's you're under the first reflector, above the second reflector, from the formula, you understand? And you can see in the formula, you understand? A1, A2, a little deeper than A1, a little shallower than the second. So that mathematics, when you see what's contributing to the image, all the multiples don't. Okay? That's the analysis that goes along with those figures. Yes? And then we don't have the one under the R2. In other words, there's a similar mathematics that gets you under the second. Okay, so that's wonderful. So when you have an accurate discontinuous velocity, if you had such a thing, you would image with Claerbout III, multiples won't. You can leave the multiples out, you can put the multiples in, they will not make any difference. Not for your image. If you're looking for experiment, yes, different. Not for the image. If you have a smooth velocity, yes, then every multiple will give you a mislocated event. Yes? That's why we got to get rid of them. Because we can't give an accurate. If we could give an accurate, we wouldn't have to take them out, because they'd give no harm. Did you hear it? That said, if we could give an accurate discontinuous velocity, just put your data in. Yes? You don't have to take multiples out. The reason we have to take multiples out is in practice, we need smooth. And we want to get, and every multiple will give you a false image. Yes? Clear? Okay. So that's wonderful, except what about when you have missing primaries? Yes? So let's talk about that. Now we're going to see value of Claerbout II. Its lack of definitiveness in some way gives it a value, because it can be interpreted differently. See, Claerbout III is so rigid, so defined, that you can't play a game with it. The Claerbout II, the up and down coincident, time, space coincident of up and down. We have different definitions, yes? Some denominators, some, so that looseness, which is troubling in some way, presented an opportunity for people. They said, well, you'll see in a second, let's interpret down and up different than what really migration is. Migration, if you think about the earliest view of migration was, you have an event in time, you want to know, put that migrated to where it belongs on a reflector. One event in time to one reflector, 1 to 1. That's a thing only makes sense for primaries. Yes, that thought, that map. Yes, and here Claerbout III tells you it's consistent with that. Yes. Okay. So let's talk about the imaging with primaries. So here's a Claerbout II kind of form where you go forward here, back here, and do use a formula like Dan would have us do with the up and down and complex conjugate, the down wave. And sure enough, you'll get an image, and you can use that amplitude, and you get the image to right there. But, and you get, for that same problem, you can do that with exploding reflector or Claerbout III. You get the same exact answer as this, forward this, back this, make it time-space coincident. Okay, that's what we just did. Now, what these capable people did is they said, let's look at this problem. Imagine you have a multiple here, which is deghosted. Very important to deghost. You have to have, that's why they talk about separated waves. That's why we're talking why deghosting and the particular deghosting that we're providing here, X omega, could benefit this. This requires an accurate deghosting. Not just deghosting, but very specific. The multiple here, completely deghosted. Source deghosted, receiver deghosted. There's another event that we want. We want this event in your data. Yes? That event on one side. So on one side of the machine is going to be this. The machine meaning there's an up and down. There are two waves. Yes. On one side is a completely deghosted multiple. On the other side, instead of this down wave, this is going to be the down wave. Yes? This is going to be the up wave going back. This is going to be the down wave going forward. And they're going to be looking for each other. Yes? Looking for each other, Claerbout II style. Yes? So this guy that it requires a source deghosting and only a receiver ghost. Don't put that in. Yes? So it's very specific in terms of up-down separating waves, yes? In terms of the input. So on one side will be, you put all your data like this. On the other side will be completely deghosted data. Yes? Completely deghosted. And you go through this procedure, which is described here, treating this as the wave which was originally thought of to be a primary, right? An up wave. In other words, you take the time-space coincident of an up wave and a down wave, this being the down. Clear? The down originally was a direct wave for the primary, yes? And everybody understands? They used the thinking that was originally thought of by Claerbout for imaging primaries, yes? And apply that up-down to that breakup. And the objective is to get an approximate image of this unrecorded primary, yes? So this is assumed to be recorded, this is assumed to be recorded, and this is what is being sought. And that is achievable if you go to a deeper, and Chalmar will show you that, if you go to a deeper sought after, you have to have the velocity. Not just this, but to where it is. Otherwise, you're not going to get an approximate image of that unrecorded primary. Yes? And you will have to treat this event in your migration, in your going back, as back through C0 and C1. Okay. So, and then you see, you have a formula. You just treat one as though it was an up wave, the multiple as an up wave, and this that kind of primary, this guy in that complex conjugate the down, use the up, do the usual Claerbout II, and go the old, and you get the location, and that's why they called it an approximate amplitude. And Dan and Nizar and everyone else will tell you, use it for structure only.
We'd also change the imaging condition to do spectral ratios, not just cross correlations.
So what we have now has that. So it's possibly advanced beyond that, but it has requirements. Okay. So this shows first value. What is the value here? If you don't have a primary, yes? If you don't have a primary, then it gives you an approximate image of an unrecorded primary. As long as you have, at least from my understanding, I'm going to need to have some primary and some offset. Otherwise, I won't get that velocity.
You have to have down.
Yes. In other words, if it's completely invisible, yes, at that reflector, you're stuck. In other words, you have to have, again, I'm not expert, but Dan is, you're going to need, let's say you want to extend this image. I need a primary that you do have to do velocity analysis.
That's not completely true. You can actually use the multiples to do velocity analysis.
Okay, well, I'm saying, to my understanding, yes? But there is some velocity analysis needed. It would be interesting to know how you use multiples. But I'm giving you my view of how it works, yes? Or my understanding of how it's carried out, yes? So again, that's just a picture of that. This is, we have permission from PGS to show this result from the Tronus, and you see the advantage before and after, yes, using that procedure. So here's the chart now. The chart is, you get reflection data, you go through all the things we say, including multiple removal. You get, from multiple removal, you get recorded primaries. Yes? We're not making, by multiple recorded, I mean you can extrapolate, interpolate, do, yes? But this is, as after you get rid of all the multiples, this is what you're going to get, yes? Basically. Then with these recorded primaries, you can do a velocity analysis. You need the velocity analysis for what we call Claerbout III, yes? Down here. You can go back up here with the velocity and take your data which are, go back up here with the velocity and take that reflection data, which has not been deghosted yet, if you want to do specific types of wave separation, yes, on one side and the other. Start over here and get an enhanced structural image. Structural image using primaries for getting an approximate image of a primary, that you did not record. Okay? If this needs to be corrected at RQ, I'm happy to learn about it. I'm saying, what we did was, I was trying to look at the literature and do analysis to figure out what's going on. Yes, by doing analytic examples, understand? Put a multiple, do this, do that. Just try to understand. So we definitely need a velocity. If you use multiples to find, you do, if you can do velocity analysis with multiples and get a discontinuous velocity, that would be very interesting. So we'd like to know exactly what that velocity is. I would be interested. So anyway, this is an adjusted chart, yes? Usual our chart doesn't have this line, yes? So that line says, if you go through all this, get yourself some primaries, get a velocity, go back up there, and then use that velocity in the sense that I just said. That multiple has, if you want, at least my understanding is, if you want that multiple to give you an approximate image of the unrecorded primary, you need its velocity. You migrate the multiple with that velocity. So you'll, Chow, you're going to show a result with C0, C1? You are? Okay, so you'll see that, you understand? A deeper primary that's trying to be reconstructed. Okay. Are there any questions?